NASA's Explorer mission launched as the beginning of an incredible journey into space, proving that we can monitor Earth, our solar system, and even deep space. After 46 years, these extraordinary spacecraft still provide scientists with groundbreaking insights, despite having memory that's 3 million times smaller than our smartphones and operating at speeds significantly slower than our 5G networks. Nonetheless, these resilient probes remain at the forefront of space exploration. Recently, Explorer 1 made an astonishing discovery in interstellar space that challenges everything we thought we knew about the universe. But what did it find, and how does it reshape our understanding of the cosmos? To appreciate the magnitude of this discovery, let's go back to the origins. On September 5, 1977, from Cape Canaveral, Florida, Voyager 1 embarked on its space journey, launched by the powerful Titan rocket. Just 15 days prior, on August 20, 1977, its twin Voyager 2 set off as well. Their primary mission was to study the large gas planets, Jupiter and Saturn, and their moons. But these Voyagers far surpassed their original mission, venturing into our cosmic neighborhood and setting numerous records along the way. They have now traveled further from Earth than any human-made object in history and have even entered interstellar space, a region of the universe never explored before. These two space pioneers, Voyager 1 and Voyager 2, are currently over 12 billion miles away from Earth. Remarkably, they continue to send back astonishing data, most recently discovering something that no one could have anticipated. Decades ago, these twin spacecraft thrilled scientists with insights from Jupiter's and Saturn's moons, which were once thought to be barren like our moon. Voyager 2 was the first to fly by Uranus in 1986, and just 3 years later it passed by Neptune, making it the only spacecraft to have done so. To conserve power, NASA turned off unnecessary components and heaters, allowing these spacecraft to function until at least 2030. For the scientists involved, this journey has been a blend of pride and bittersweet anticipation, as new surprises continue to emerge from these distant explorers. The data sent back by Voyager 1 and Voyager 2 has proven to be a treasure trove of information, sparking numerous discoveries and igniting public excitement about space. Built with exceptional durability to withstand the harsh conditions of space, they captured clear images and valuable data even before reaching the outer planets. Early on, Voyager 1 transmitted stunning images of Jupiter, showcasing its swirling clouds and iconic Great Red Spot. But it was the groundbreaking discovery on Jupiter's moon Io that captivated scientists. Io, much larger than Earth's moon, was found to be the most volcanically active body in our solar system. Together, the Voyagers took over 33,000 images of Jupiter and its moons, revealing the planet's dazzling beauty and the varied landscapes of its moons. The discoveries didn't stop with Jupiter. The Voyagers observed that Jupiter has faint rings and confirmed that Europa, one of its moons, has a thick icy crust over 60 miles deep, raising questions about whether it might harbor life beneath its frozen surface. As the Voyagers left Jupiter, they used the planet's gravity as a powerful boost, propelling them toward Saturn and eventually freeing them from the Sun's gravitational pull, allowing them to travel even further into space. Following different paths, Voyager 1 approached Saturn's moon Titan, which has a thick, hazy orange atmosphere, sparking scientific interest in its mysterious chemistry. Voyager 1 then journeyed beyond the planets, while Voyager 2 continued its exploration. In 1986, Voyager 2 flew by Uranus, discovering 10 new moons, and 3 years later, it reached Neptune, providing detailed insights about this distant ice giant. Voyager 2 measured Neptune's winds, the fastest in our solar system, clocking in at 1,000 miles per hour. When it neared Neptune, just 2,980 miles away, it revealed fascinating details about Triton, Neptune's largest moon, one of the coldest places in our solar system, with temperatures dropping to a frigid -391 degrees Fahrenheit. Triton was also found to have ice volcanoes that spew nitrogen gas and icy material, making these distant worlds unexpectedly dynamic and intriguing. One person who played a crucial role in preserving Voyager's legacy was the renowned astronomer Carl Sagan. He pushed for one last series of photos before turning off the cameras. Taken on Valentine's Day in 1990, these images provided a final look back at Earth, with the most famous being the pale blue dot image taken from 3.8 billion miles away. In it, Earth appears as a tiny speck, a pale blue dot against the vastness of space. Even after 40 years, these spacecraft remain active, sending back valuable data from the far reaches of space. Space exploration has relied on a crucial system that enabled continuous communication with our brave Voyager probes as they journeyed into the unknown, the Deep Space Network, DSN. This network isn't as glamorous as a spaceship, but it's essential to the mission. Imagine the DSN as a vast network of radio antennas located in places like California, Spain, and Australia. Some of these antennas are as large as 70 meters across, functioning like cosmic megaphones that allow us to stay in touch with spacecraft traveling far beyond Earth. Let's dive into its role in the Voyager missions. The Voyager probes, equipped with cameras and sensors, serve as our eyes and ears in space. To receive the data they send back and guide them, we needed a robust communication system. That's where the DSN steps in. Imagine Voyager 1 heading to the distant edges of our solar system, sending a faint signal back to Earth. It's a tiny signal traveling at unimaginable speed, but by the time it reaches Earth, it's extremely weak. The DSN's giant antennas are trained to detect that faint whisper from Voyager and convert it into usable data for scientists. The DSN doesn't just receive messages, it also transmits commands to the spacecraft. This two-way communication allows researchers and engineers to update mission plans or give the spacecraft new instructions. It's like an ongoing conversation between Earth and the most distant human-made objects in space. One amazing feature of the DSN is its round-the-clock operation, constantly listening for these distant signals. This network isn't just a series of antennas. It's like a lifeline keeping the Voyager missions active, even as the probes journey far beyond our solar system, venturing into the uncharted realms of interstellar space. Interstellar space is closer than the outer limits of our solar system, which you can imagine as a large bubble of objects held by the sun's gravity, like the far-off Oort cloud. This cloud extends partway to the nearest star, but it will take Voyager around 300 years to approach its edge. The boundary of interstellar space begins where the solar wind, charged particles and magnetic fields from the sun, fades out. This solar wind forms a protective bubble called the heliosphere, which eventually encounters pressure from interstellar matter at a boundary called the termination shock. Beyond this lies the heliopause, marking the edge of our solar system. Early estimates once placed it near Jupiter, but more accurate calculations in 1993 set it much farther out. Voyager 1 reached the heliopause about 20 years later, detecting an increase in plasma density. Voyager 2 reached this boundary in 2018, but surprisingly found no change in the magnetic field, a detail that challenged existing theories, which expected variations tied to the sun's 11-year cycle. Voyager's real-time data has helped scientists refine their models of the heliosphere's interaction with interstellar space. In essence, as our sun transitions from a hot ionized zone to a partially ionized region of the galaxy, it's like moving from calm waters into a turbulent sea, where magnetic fields bend and twist in ways previously only theorized. Eventually, the Voyagers will leave this chaotic zone and enter the pure interstellar magnetic field, marking a new chapter in their journey. Although both probes still have functional instruments powered by a system that converts plutonium's radioactive decay into energy, their power is decreasing by about 4 watts per year. This means the team is operating in crisis mode, carefully managing every bit of power. It's fascinating to watch the Voyagers continue on their journey, but soon we'll have to say goodbye. Voyager 1 is expected to pass near Proxima Centauri, our closest stellar neighbor, in about 16,700 years, while Voyager 2 will make its own star encounter after about 3,600 years. From there, they'll continue to orbit the galaxy for billions of years, long after the sun and heliosphere are gone. All of this started from that small pale blue we call home, and it's as if their cosmic journey will never truly end. The Voyager probes may still be out there, resilient in the vastness of space. They might even send a final message in some form, though not on the radio. Instead, they each carry a special artifact, a golden record. Made of copper, with a gold-plated surface and encased in aluminum, these records are like old-school tech with a modern twist. They hold about 90 minutes of music, from Bach's Brandenburg Concerto No. 2 to Chuck Berry's Johnny B. Good, along with images of children, dolphins, artists, sunsets, crickets, rain, and a mother kissing her child. President Jimmy Carter, who was in office when the Voyagers launched, left a message on the record. "We cast this message into the universe, hoping that one day, when we solve our own issues, we can join a community of civilizations out there." These records are a message of hope and goodwill from Earth to the vast, magnificent universe. The Explorer missions still rely on old 8-track tapes, which may sound surprising in today's digital age, but they were cutting edge in their time. Back in the early days of space exploration, digital storage as we know it was in its infancy. Engineers needed something durable and reliable to store critical data, and 8-track tapes fit the bill perfectly. Although 8-track tapes were widely known for music in the 1970s, on these missions, they store priceless scientific data about planets, moons, and even interstellar space, making them essential for some of the oldest and most profound insights into our solar system. The resilience of the Explorer spacecraft is remarkable, given the harsh conditions they encounter. From extreme temperatures to intense space radiation, these probes continue to perform like seasoned explorers, enduring the test of time and technology. Their continued success is comparable to sending an elderly grandparent on an expedition to Antarctica, and not only surviving but thriving. A key to the success of the Explorer missions was the strategic use of gravitational assists, also called gravity assists or slingshot maneuvers. These maneuvers involve using a planet's gravitational pull to accelerate and direct the spacecraft, saving fuel and increasing speed. Instead of solely relying on their engines, these spacecraft engaged in a cosmic dance with the planets, using their gravitational pull to propel themselves deeper into space. Imagine Explorer 1 approaching Jupiter, a massive gas giant with a gravitational force that can give the spacecraft a boost. NASA engineers at the Jet Propulsion Laboratory, JPL, timed Explorer 1's approach so that it passed by Jupiter at just the right angle and speed. Jupiter's gravity pulled on the probe, accelerating it forward and allowing it to gain the velocity needed for the next leg of its journey. A slight miscalculation, however, could have spelled disaster by throwing the probe off course, so precision was key. Thanks to these meticulously executed gravity assists, both Explorer 1 and Explorer 2 embarked on remarkable journeys through the solar system. Explorer 2, for instance, received boosts from both Jupiter and Saturn to reach Uranus and Neptune. These gravitational assists were instrumental in enabling the grand tour of the solar system, allowing the probes to achieve extraordinary feats that would have been impossible with their engines alone. The concept behind gravity assists is simple, but executing it requires precise calculations. If the spacecraft missed even one of these crucial boosts, it could jeopardize the entire mission. Fortunately, the scientists and engineers in charge managed each maneuver with exceptional accuracy, enabling Explorer 1 to enter interstellar space and Explorer 2 to follow close behind. Behind each of these gravity assists was not only sophisticated planning but also insights that expanded our understanding of deep space. The Deep Space Network, DSN, a system of large antennas, played a crucial role in maintaining communication with these distant explorers, ensuring that they could send back data from the far reaches of our solar system. The legacy of the Explorer missions goes beyond the groundbreaking gravity assists and innovative use of 8-track tapes. It reflects a deep commitment by scientists and engineers to push the boundaries of what's possible in space exploration.